Hi, this is an example problem about a parallel plate capacitor. Pause for a moment and read the question. So we see that there are two plates here. They're in profile, right? They extend, into the screen. And we can see that there are electric field lines drawn from the plus to the minus charges. We can also see that the field lines in the central region between the plates, they are straight lines or equally distantly spaced. That means the electric field is constant in that region. In addition, we see that there are some equipotential lines, equipotential surfaces that are drawn, and they are drawn with a spacing of 25 volts, the positive plate at 100 volts, the negative plate at 0 volts, right? Electric potential always higher by the positives. All right, let's see how we can solve for part A in this problem. Part A says, in which direction, right or left, does the charge move spontaneously? So we are essentially taking this Q0 charge plus 2 microcoulombs. We're going to place it at point I. So here's our little charge here. Put it at point I, Q0. Which way is it going to move spontaneously if it's released from rest? Well, this is a positive charge, right? It doesn't like the positive plate, likes the negative. It's naturally going to go ahead and move spontaneously towards the negative plate, right? So we can go ahead and write right. That is the answer for part A. Let's look at part B. If the charge moves to point F, which is the change in its, what is the change in its electric potential energy, right? So delta PE, right? Remember that we can write that as PE final minus PE initial. And we have a formula for the electric potential energy. That's going to be Q times V final minus Q times V initial. And in fact, in this case, what we can do is we can factor the Q out. We can just multiply Q times the change in the electric potential. We call this guy the electric potential difference or the voltage. And in this case, so we can calculate that as well. Because the electric potential difference here, right, that is V final minus V initial. And those are labeled on the equipotential lines, right? V final right here, 25. So let's put in our value for Q plus 2. Remember that this is a microcoulomb multiplied by V final was 25 volts. I'm going to make that joules per coulomb. Same units. And V initial, here it is, 75. So minus 75 joules per coulomb. When we put that into our calculator, we're going to get an answer here. Minus 1.0 times 10 to the negative fourth joules. Again, because the coulombs canceled out, we're ended up with joules. So notice what this means. It means that this positive charge released from rest, it spontaneously moves downhill to a lower electric potential. And that's because its potential energy is decreasing. Just like if you drop a basketball, it's going to naturally fall from higher potential energy above to lower below. Let's look at part C. We're given a mass of Q0 and we're asked what is its speed when it arrives at point F. Ignore air resistance. Ignore air resistance is important because these little charges, typically if they're moving through the air, they're going to lose their energy as they move through the air. Think of lightning, right? Charges are dumping from a cloud to the ground or something, right? They're heating everything up as they pass through. You got a lot of sound, a lot of heat, a lot of brightness. So it's not all going into speed. But if you ignore air resistance or if you put it in a vacuum, then you can make it all go to speed. So let's go ahead and see how we're going to do this one. We're going to use the conservation of mechanical energy to do this. So delta KE plus delta PE, conservative force, electric force, they sum to 0. This is your conservation of mechanical energy. We know what delta PE is. We just calculated that in part B. KE, let's look at this. Initially, what is the initial speed here? It's 0, right? Because it starts from rest. Key point there. Now, I don't like to confuse electric potential V with speed, so when I do speed, I try to do a little curly V, a little script V. Now we are looking here at the point F. What is V final here? What is the speed at the end there? Well, we can go ahead and write down delta KE as being 1/2 m V final squared minus 1/2 m V initial squared plus delta PE equals 0. And we just said that the initial speed is 0, so that whole term is gone. And if we want, we can go ahead and write this as 1/2 m V final squared. I'm going to go ahead and subtract the delta PE from both sides. Bringing it over, I get this. And finally, we need to go ahead and solve for V, right? So let's just do a little bit of algebra here. We're going to go ahead and multiply by 2 and divide by m on both sides. Get rid of those m's and those 2's. And we're going to be left with a V final squared is equal to, well, let's just go ahead and take the square root right now, negative delta PE times 2 divided by m. And now all we need to do is go ahead and plug in our numbers in here because we know all these values, and then we'll end up getting our answer. Negative the delta PE from part B, minus 1.0 times 10 to the minus 4th. I'm going to write joules as kilograms, meters squared per second squared. Notice that the negatives are going to cancel, which is good. Multiplied by 2, divided by the mass. What is the mass equal to again? 0.5 times 10 to the minus 6th kilograms. Kilograms will cancel, and when we take the square root of the meters squared times second squared, we will get meters per second, and the answer comes out to 20 meters per second. All right, finally we're going to go ahead and look at part D here. Part D says, what is the magnitude of the constant electric field between the plates and the electric force that acts on Q0? Again, we see that these lines here, they're all in the same direction. They're all equally spaced. That means that this E here in the region, this guy is constant. Now, whenever we have a constant electric field, there is a relationship between the electric potential or the electric potential difference, the voltage, and the electric field. Notice as we move, as I go from positive to negative, I'm going from high electric potential to low electric potential. And that's always the way it is. As you move along an electric field line, you go from high to low. Now there's a formula when the electric field is constant that allows us to relate the change in delta V going from high to low. It's equal negative times the constant electric field times the distance that you move. So we can go ahead and use this little equation here. For part D. And let's just go back and read part D again real quick. What is the magnitude of the constant electric field? Well, we want the magnitude here between the plates and the electric force that acts on Q0. Well, we were told that the distance between the plates here, from here to here, that is equal to 5 centimeters. That is what we call delta X in that equation. A lot of times we also just call this distance D. And since we are dealing with magnitude of electric field, we can take the absolute value of everything here. which allows us to write this in a new way. Absolute value of delta V. So the absolute value of the voltage is equal to EX times delta X, as I get, sometimes we write that as D. And now we can calculate what E is equal to. So electric field strength here, I'm just going to, the magnitude, I can get rid of the X component here. And so the electric field strength is going to just be equal to the change in the electric potential, the voltage, the absolute value, divided by the separation between the plates. And in this case, we can calculate those things. The voltage between the plates, right, it's going to be 100 because it's 0 at the low and 100 on the high. So delta V in this case, we might write it like this: 100 volts at the positive plate minus 0 volts at the negative plate, divided by the distance, 5 centimeters. We got to convert that to SI units. And we're going to get an answer here that's equal to 2,000. And look at the units, volts per meter. That's another set of units that you can use for electric field. We also know that we can write this as newtons per coulomb, and let's just check that out real quick. So a volt per a meter, that's equal to a joule per coulomb over a meter, which is equal to a joule is, remember, a kilogram meter squared per second squared. Bring the C to the bottom. We can cancel one of the meters out. A kilogram meter per second squared, that's a newton. So in fact, either of those are good ways to represent the electric field. This set of units shows us how quickly the electric potential changes across distance. The bigger that electric potential changes, the bigger the electric field strength is. But when we're doing, for the second part here, what is the force that is exerted on the charge? Positive 2 microcoulombs. So again, to get the force from the field, we just multiply Q0 by the field. We're doing magnitude, so we just take the magnitude. Now in this case, I'm going to go ahead 2 times 10 to the minus 6 coulombs, and I'm going to go ahead and choose these units for electric field because that helps me get a better idea of how the electric field transmits force to that charge. Plugging that into the calculator, we get a value equal to 4 times 10 to the minus 3rd newtons.